Hi, as a warm-up, I'm going to show you the weak law of large numbers, which of course we know as the strong law implies the weak law, but nevertheless it's going to be nice and easy with characteristic functions. Weak law of large numbers. Okay, so let x1, x2 and so on be IID with finite mean. And actually their means I'm just going to denote by m. And as usual, Sn will be the sum of the first n of these guys. Okay, so then the weak law of large numbers states that Sn over n converges weakly to this mean m. Let me actually expand this a little bit. So what is weak convergence? Is that the distribution functions converge, right? So that is that the probability that Sn over n is further away from m than epsilon goes to 0 as n goes to infinity for every epsilon. Convince yourself that this statement is exactly that the characteristic functions converge to the step function, which is stepping at m. Okay, let's prove this with the characteristic function. The proof goes like this. Take phi of this Sn over n random variable. What is this? That's the expectation of e to the I t Sn over n. If I bring the n over to the t, you can easily see that this is also the characteristic function of Sn itself taken at t over n. Sn is the sum of IID random variables, so this is going to be the characteristic function of just one of them taken at the same place t over n, however raised to the nth power because we have an n-fold convolution here. Okay, I'm going to drop this notation x1, so I'm just going to denote this simply phi. And now let's make a little calculation of what this thing is. So what is phi? Let's bring back the lemma which we just proved in the previous video and apply it at n equals to 1. N equals to 1 tells me that we have these 0 and 1 terms under the Taylor expansion and an error term which looks like t to the 1 times something little of 1. Okay, so let's put that in here. The first term is when k equals to 0 is just 1. That's the k equals to 0 term from here. K equals to 1 gives an it times the first moment. It times the first moment, except we have to be a bit careful because instead of t, we're working with t over n now, times the first moment. And then there is an error term which is little o of t over n. It's in the way it was formulated in the lemma, it's essentially t. This n is not the same as that other n. So it was essentially t to the first power times something that goes to 0 with t. Instead of t, we are working with t over n. So little o of t over n is exactly the same thing. Now all we need to realize is that this expectation is what we called m before, and then the limit of 1 plus constant over n to the n converge is, this limit is exponential of all of these factors, which is I, t, and m. And little o, something sublinear in 1 over n, will not play any role in the limit. So as n goes to infinity, we have this limit here. Now this limit is a characteristic function. It is continuous at 0. It is a characteristic function of what? Of the almost surely constant random variable. Of the almost surely constant m random variable. Therefore, the continuity lemma tells us that the Sn over n sequence weakly converges to this distribution, and that's exactly the strong law of large numbers. So continuity lemma now concludes this proof. It says that the law of Sn over n, of which we have the characteristic function to start with, will converge to the law of the random variable with this characteristic function, which is constant n, almost surely.